Hi guys. Okay, in this video we're going to talk about what you can do with truth tables. The previous videos I've been telling you about how to complete a truth table. Now we're going to learn what you can do with them. So just take a step back and think about the big picture here. Um, let's think about the skills you've been learning. So our ultimate goal here is for you to be able to take an argument in English or some other natural language, symbolize that argument in a formal language, in this case TFL, in the second half of the class FOL, and then use some formal tools on the symbolized sentence to test whether the argument is valid. And that'll tell you whether the original English argument was valid. So you have learned so far, you've already learned how to symbolize English sentences in TFL. You've now learned how to apply a certain kind of tool to sentences in TFL, that is, how to complete a truth table. But we haven't yet turned that into a test for validity. We haven't said, okay, once you've completed the truth table, look at it, and here's how you'll be able to tell if it says your argument is valid or not. That's what we're going to work on in this video. Okay, so the concepts we're going to get onto are on the screen there: tautology, contradiction, tautological equivalence, etc., etc. Just a reminder that word tautological, as we use it in this class, means something like in virtue of a truth table. So wherever you see tautology, think truth table. So a tautology as a sentence is something that's logically true because of its truth table. So something whose truth table tells you this can never be false. And likewise, a tautologically equivalent pair of sentences is a pair of sentences that's equivalent, and the truth table tells you so. Tautologically valid argument, it's valid, and the truth table tells you so. Okay, we'll get onto those things in a second. Before I give you the specific tests for each of these things, I want to talk about what a truth table does, right? What the point of one is. Okay, so think about it this way. When you start setting up a truth table, always the first thing you do is you get something like what's on the screen now, right? You look at the sentence or sentences you're interested in, you find all the atomic sentence letters that appear there, and you collect them over on the left. You count up how many there are. That tells you how many rows you're going to have, right? 2 to the power of the number of atomic sentences. And then you make sure that you get all of the 2 to the power of that number combinations of truth values for each of the atomic sentences, right? So if you have 3, like here, then you're going to have 8 rows. You'll need a row where they're all true. You've got rows where 2 are true and 1 is false. You've got 3 rows where 1 is true and 2 are false, and a row where all 3 are false. You got to make sure they're all there. Okay, why are we doing that? Here's why. I want you to think of these rows. The rows of the truth table are telling you about different ways the world could be, different possibilities, if you like. Okay. Here's the nice thing about truth functional logic. Because our logic is truth functional, remember, truth functional means the only thing that matters in determining whether a given sentence is true or false is the way the sentence is set up, so which connectives are in there and how things are combined, and whether the atomic sentences involved are true or false. That's it. That's all you need to know. That means, although there may be infinitely many different ways the world could possibly be, there are only 8 that matter if you're dealing with a sentence that has 3 atomic sentences, right? We can group all those infinitely many possible configurations of the world into 8. The ones where A, B, and C are all true, the ones where A is true, B is true, C is false, etc., down the list. Okay, so I want you to think of rows of the truth table. I really want to emphasize this. I want you to think of rows, horizontal rows of the truth table as individual possibilities, ways the world could be. So when you see in a definition of one of our concepts words like possible or impossible, you're looking for rows of a truth table. If a definition of a concept says, such and such is, let's say, consistent, a collection of sentences is consistent if it's possible for them all to be true at once. That means, well, if it's possible, then there is a possible way the world could be where that thing happens. If we're looking for a possible way the world could be, we're looking for a row of the truth table. So if the definition of consistency says it's possible for these sentences to be true all at once, that means For tautological consistency, we're looking for a row of the truth table where you get all of the sentences true. Okay, that's how it works when you see possible in one of your definitions. When you see impossible, be careful. So for possibility, we're looking for a row that shows something. When you see impossible, we're looking for the absence of a certain kind of row, which means you have to check the whole thing. So if you have something that says like, okay, tautology. A tautology is something that's, it's impossible for it to be false. If it's impossible for it to be false, that means there shouldn't be any row. None of these 8 rows should have false. That's an ugly false. That can't happen. False, no, that can't happen. In other words, each of these rows must have true. Right? If it's impossible for your sentence to be false, then the only kind of possibility is true. That means we're going to be looking for true all the way down. Okay. This is really important, especially when we look at validity, because remember, validity is defined in terms of impossibility. I'm making a mistake myself. What makes an argument valid is if it's impossible to have a certain combination of truth values, namely all true premises and a false conclusion. So if you want to show something is valid, you have to make sure none of the rows of your truth table have true premises and a false conclusion. Okay, let's look at some examples. So I've just done some of these truth tables just so I can show you what I'm looking for in the truth table. This video isn't about how to set up the truth table, it's about how to read it once you see it. So here's a sentence that we did in a previous video. We did the truth table for this, so I'm skipping to the results. A arrow B or B arrow A. So there are only 2 atomic sentences here, A and B, which is why we have 2 to the power of 2 sentences, 4 rows. So 4 possibilities, either both true, 1 true and 1 false, or both false. And when we fill out the truth table, we get true all the way down. We get a column of all trues. What does it mean for a column to be all true? That means in every row, you've got true. In other words, in no row do you have false. So it's impossible. There is no possibility where this sentence is false. So it's a tautology. Ooh, that's very adamant. Didn't realize I had caps lock on. I'm going to stick with that. So a tautology remember, a tautology applies to a single sentence. A tautology is a sentence where you get true all the way down the truth table underneath it. Every single row has true. Conversely, a contradiction is a sentence where you have false all the way down, because a contradiction is something that it's impossible for it to be true. So here we have a contradiction. A and not A. Can't ever be true. Okay. Remember, there's a third thing. Not every sentence is a tautology or a contradiction. The ones that are neither are contingent. What is a contingent sentence? It's one that could be true or it could be false. So if you want a truth table for showing that something is contingent, then it's got to have at least 1 row with true and at least 1 row with false. In other words, you've got something that fails our test of a tautology, which was where we checked, do you have true all the way down? And it fails our test of a contradiction. It's got false all the way down. Okay, I'm going to move on. Next concept, equivalence. Equivalence is something that holds between a pair of sentences. You've got to be looking at 2 sentences and you're asking, are these 2 equivalent? In our case, we're asking, are they tautologically equivalent? Because we're doing truth tables today. So take these 2 sentences, sentence 1, sentence 2, work out their truth table on the same table. So we've got multiple columns over here on the right-hand side. And now we're checking, okay, the definition of equivalence is something like this. It's impossible for the 2 sentences to have different truth values. So this time, I'm not concerned with columns. I don't care what the shape of the columns are, right? This one can have whatever combination of truth values it likes, just as long as I get exactly the same ones over here. Why? Because I'm checking impossibility. Impossible for these 2 to be different in truth values. So I have to check all 4 possibilities. In this one, are they different or the same? They're the same. What about this one? The same. They're both false. Again, they're the same here. Again, they're the same here. That's all of them. There is no possibility other than these 4. And all of these possibilities are ones where they have the same truth value, so it's impossible for them to have different truth values. So these are tautologically equivalent. By the way, notice this. Notice the sentences I've chosen. We have not A or B in brackets. And then over here, no brackets, we have not A and not B. There's a general pattern here. When you have an and or an or in brackets and you have a not outside it, you can take the brackets off as long as you do two things. You put the not on both things, so on both A and B, and you change the or to an and, or vice versa. So we've changed, here's an or, here's an and we took the brackets off and put the negations on the two conjuncts or disjuncts. Okay, notice that you have to do both of those things. Here's a set of sentences that are not equivalent, if I'm going to the right page. So here, these two sentences, I've again got not bracket A or B, and this time I took the brackets off, put the negation on the A and on the B, but I didn't change from or to and. And if you work out this truth table, you'll get, well, so not A, that's false here. Not B, that's false here. When I do an or rule on false or false, I get false. But now this next line, not A, that's still false. Not B, that's true now. And remember, the or rule says you just need at least one of these two things to be true. So false or true is true, which is different from what we get over here. So if I ask myself, are these two sentences equivalent? Again, I'm asking, is it possible or is it impossible for them to have different truth values? I find out, oh, look, here's a possibility where they have different truth values. So it's possible for them to have different ones. I can stop now. I don't have to check the rest of the table. As long as I've found one way that it's possible for them to have different truth values, I can end my test and call them inequivalent. Is that a word? I think that's a word. Let's just call them not equivalent. These two sentences are not equivalent. Doesn't matter what's happening with these. Oops, didn't mean to do that. It doesn't matter what's happening with these later rows. I've already found a row that shows this thing is not equivalent. If you happen to hit on this row first, that would count too. But, okay. This is the difference between possibility and impossibility. Remember, for equivalence, when I want to show these things are equivalent, I want to say it's impossible for them to be different, which means I have to look at the whole table, all four possibilities. When I'm saying they're not equivalent, I'm saying it's possible for them to be different. So just one way that it's possible is enough to show that it's possible. An extra way that of making them have different truth values is just overkill. Okay, validity, the big one, the headliner, the one that we're all here for. Here's an argument. How can you tell it's an argument? There are various ways to show that something's an argument, but look, we have multiple sentences, 1, 2, 3, and I've used this sign with the 3 dots in this configuration in a sort of upward pointing triangle. That's a sign that means therefore. If you have a therefore in your argument or in your suite of sentences, then the thing after it is a conclusion, and if you have a conclusion, then you have an argument. So look for those therefores. Make sure that if you're symbolizing an argument from English, then your result in TFL will also have a therefore in it in some kind of way. You don't have to use the 3 dots. You can write the English word therefore, that's fine, but you have to have some indication. Okay, so here's what we do. We do the truth table for all 3 sentences. A and B here, those are atomic, so I'm just copying over their respective columns. A arrow B, that's just the arrow rule. Okay. Truth table is complete. I want to know, is this valid? Valid means it's impossible to have true premises and false conclusion. Impossible. So I'm checking all 4 rows. Okay, row 1, I have true premises and true conclusion. That's okay. Remember, all I'm concerned with, I want to make sure it's not possible to have true, true, false. So on each row, I'm looking at it and asking, does it say true, true, false? Does it say true, true, false? I don't care what it says instead. It could be true, true, true. It could be false, false, false. It could be false, true, false. Anything other than true, true, false is okay as far as validity is concerned. I just have to make sure there is no line where I get true, true, false. So this row is not true, true, false. This row is also not true, true, false because there's a false over here. This is also not true, true, false. This is also not true, true, false. None of them are true, true, false. Hooray! So this is a valid argument. Okay, notice, I really want to emphasize this point. When you're showing with a truth table that an argument is valid, you have to point to all of the rows. You need all of them to be done. You have to make sure none of them are true, true, false. Let's look at an invalid argument, though. So if valid arguments was about something being impossible, and invalid argument is about something being possible. So our argument before was if A then B, A therefore B. Our new argument, which will turn out to be invalid, is if A then B, B therefore A. So I've swapped the A and B from premise to conclusion. Okay, so here's your truth table. Now I'm going to go through all the rows. I'm going to ask, do I get true, true, false? So up here, true, true, true could be valid. Next row I get false, false, true. That's okay. The argument still could be valid. Third row I get true, true, false. Aha, okay, I found it. I'm done. That's it. As long as there's something like this, sirens go off. I mess up my page and I say, this is valid. And I'm going to erase some of that because that was unfortunate. Let's do something a little more restrained and say, look, I'm putting stars around this. I am going to circle it and say, look, I've got true, true, false. The premises are true and the conclusion is false in this possibility. Remember, a row of the truth table is a possibility. It's a way the world could be. It could be that A is false and B is true. If that were the case, then your premises would be true and the conclusion would be false. Because that's possible, that tells us this is invalid. I think I wrote valid before. That was really a disaster. Okay. Let me drive this home. I'm sorry if I'm beating it into the ground. I'm actually not sorry. Come back here. Here was our valid argument. The valid argument, I had to check all 4 rows. I had to check all of the possibilities. I needed the whole truth table. To show something's invalid, I just need 1. I hesitate to say this because I worry that I'll stick with you, but here's a particular pitfall to watch out for. Notice that, so some people will say, oh, I'm going to look at the valid argument and I see, oh, I've got a row with true, true, true. That means it's valid. No, it doesn't. You know how you can tell? Here's our invalid argument and it has a row with true, 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 right? The fact that this kind of thing is possible doesn't tell you that this kind of thing is impossible. And that's the only thing we care about for validity. The definition of validity doesn't care whether you can have true premises and a true conclusion. Not interested. The only thing we care about is whether you can have true premises and a false conclusion. We want that to be impossible. Doesn't matter what else is possible. That's the only thing the definition of validity or invalidity cares about. Okay. Last concepts. Consistency and inconsistency. So here again we have a list of 3 sentences, but there's no therefore sign. So this time there's no question about validity or invalidity because we don't have premises and conclusion. We just have a list of 3 sentences. So instead we're going to ask, are they consistent? So the question about consistency is it possible to have all of them true? This time I do care about the kind of row, the kind of possibility I do care about is true, 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 right? None of them is a conclusion, so there's none that's different and special where I care if it's false while the other ones are true. I'm just asking, can they all be true at once? So if it's possible for them all to be true, then it's consistent. If it's impossible, then they're inconsistent. So check row 1. We've got true, true, false. Nope. Next row, false, true, true. True, false, false. True, false, true. None of these are a possibility where I get true, true, true. Therefore, these sentences are inconsistent. To show something's inconsistent, remember inconsistent means it's impossible for them all to be true at once. Since we're looking at impossibility, you have to check every row. You have to point to every row. Okay, here's a slightly different set of sentences. If A then B, A, B. Are these consistent? Well, hey, looky here. We've got a row where all of them are true. That's enough. I can end this. I'm done. Drop the confetti. We figured it out. Because of row 1, these guys are consistent. Row 1 is a possibility where they are all true. Therefore, there is a possibility where they're all true. In other words, it's possible for them all to be true at once, so they're consistent. Okay, that's how you test for each of these things. Goodbye.